In this problem, hydrogen sulfide is an impurity in natural gas that is removed. One method to remove it is the Claus process, seen below. So in this case, we have hydrogen sulfide plus oxygen goes to S8 and H2O. So as we look at this, before we even get into the previous parts, this is unbalanced, and so we need to make sure that it's balanced. So first things first, if we see that there are 8 sulfur on the product side, we need 8 on the reactant side, so we're going to add an 8 here. When we do this, there are now going to be 8 waters at least, and so 8H2, 8H2. When we do that, there are now 8 oxygens on the product side, and so we're going to add a 4 in front of the oxygens. So our next question is, if we started our process with 30 grams of hydrogen sulfide and 50 grams of oxygen gas, what is the ideal yield of S8? Oh, so it looks like this is going to be a limiting reactant problem, okay? So we want to figure out the limiting reactant so that we can determine what is our percent yield. So the way to do this would be to determine which of these is our limiting reactant, and that will tell us how much hydrogen sulfide we need. So the first thing we're going to determine is how much oxygen is required if we start with 30 grams of hydrogen sulfide. So we need to determine the molecular weight of all of these. So we use our periodic table. So H2S is 2 times hydrogen, which is 1.01, plus sulfur, which is 32.07. In this case, it is 34.09 grams. O2 is 32, which is 2 times 16. S8 is 32.07 times 8, which is 256.56 grams. And for water, it is 1.01 times 2 plus 16. In that case, it's 18.02 grams. So those are all of our molecular weights, which we'll use through the whole problem, or we might use. So in this case, we want to determine how many grams of oxygen we need. So we start with 30 grams of hydrogen sulfide. There are 34.09 grams in 1 mole of H2S. Now we need to convert H2S into oxygen. So we have 8 moles of H2S for every 4 moles of O2. Now in 1 mole of O2, there are 32 grams of oxygen. So once we do this, we can plug it into our calculator. Make sure that shows up. Oh, I can't see my problem. 30 divided by 34.09. Oh, that was a mistake. 30 divided by 34.09 times 4 divided by 8 times 32. And we get that you need 14.0 grams. So in this case, if we have 30 grams of this, we need 40.08 grams of O2. How many grams of oxygen are in the problem? Well, we have 50 grams in the problem. So we know that the H2S is going to be our limiting reactant. Now, I solved it using H2S. I'm going to very quickly go through how it would have looked if you had used the grams of oxygen to determine your limiting reactant, just in case that was something that you had thought about. So 50 grams of O2 divided by 32 grams of O2 and 1 mole of O2. There are 4 moles of O2 for every 8 moles of H2S that are used in the equation. 1 mole of H2S has 34.09 grams. So how many grams of this do we need? 50 divided by 32 times 8. Whoa. $50 divided by 32 multiplied by 8 divide by 4, multiply by 34.09. So we need 106.53 grams of H2S. We don't have this much hydrogen sulfide in our problem, so we know that this can't be possible. So this cannot be our limiting reactant. So we have our limiting reactant, and we're going to use that value to determine what is our ideal yield of the product. So we're going to take our 30 grams of H2S. We're going to again use the molecular weight, which is 34.09 grams and 1 mole of H2S. We're going to use 8 moles for every 1 mole of S8. We need an ideal yield. In this case, yields are in grams. So every 1 mole of S8, there are 256.56 grams. So when we plug this into our calculator, whoops, we can't see it. So we have 30 grams divided by 34.09 divided by the 8 moles. We're going to multiply that by our new molecular weight. And in this case, we get 28.22 grams. We want to make sure that we use our significant figures. If we check in the problem, there are 3 here and 3 here. So there need to be 28.2 grams of S8. Now part 2 of this asks, if you only collected 18.2 grams of S8, what is our percent yield? So percent yield is the actual over theoretical. Now, another word for theoretical is the ideal yield. So our actual yield is 18.2 grams. Our theoretical yield is 28.2. We're also going to multiply that by 100. So 18.2 divided by 28.2 multiplied by 100 gives us 64.5% yield. So we got 2/3 roughly of what we expected to get using the Claus process.